Calculus, Curve Sketching Part 2, dealing with asymptotes. An asymptote is a line or curve towards which another curve is approaching closer and closer without ever reaching it, but getting as close as is required to the asymptote. This one, the horizontal asymptote, as x goes to the left forever, negative infinity, the y value is tending towards a. The function value is tending towards a. As x goes to the right forever, tending towards infinity, the y value, the function value, is getting closer and closer to a, tending towards a. There is a vertical asymptote. This is the line x equals a. And as x tends to a from the left-hand side, this graph is climbing and the y value, the function value, is tending towards infinity. As x tends to a from the right, from a positive, the graph is tending towards negative infinity. We could flip this graph and have it tending towards plus infinity here, and flip it and have it tending towards negative infinity here. Either way around will work. So, the limit of f of x as x tends to infinity equals a. That means y equals a is an asymptote. So that is the horizontal asymptote. Meaning if you need the horizontal asymptote, find the limit as x tends to infinity of the function. Here's an example. Now, the only way this will work is if I obtain 1 over x, 2 over x, a constant over x out of this, because I know that a constant over x becomes smaller and smaller as x becomes bigger and bigger. It's a fraction with x in the denominator. So what I'm going to do is I'm going to divide top and bottom, that term, and that term by x. Like that. So I'm dividing that by x, 1, that by x, 1, that by x, 1 over x. You'll note that it hasn't changed in value at all. It's as if we've cancelled. Now, that is a constant, stays as 1. That is a constant, stays as 1. But 1 over x tends to 0 as x tends to infinity. And gives us 1. So there is the horizontal asymptote, y equals 1, or f of x equals 1. If the limit of f of x as x tends to a is infinity, or negative infinity, then x equals a is an asymptote, is a vertical asymptote. So if we have to find the vertical asymptote, we say what must x approach to make the function tend to infinity. In essence, it means what value of x to give us division by 0. There's the summary. Asymptotes. Horizontal, y equals the limit of f of x as x tends to infinity. Vertical is x equals a, where the limit as x tends to a of f of x is infinity. And don't forget that you can also have as x tends to negative infinity. We can have negative infinity there, and we can have negative infinity there, going forever to the left. Let's look at some examples. Horizontal asymptote. What I'm going to do is I'm going to take this value, this function value, and I'm going to find the limit of it as x tends to infinity. Once again, I'm going to divide by x, divide by x, divide by x, divide by x. If one of these was an x squared, I'd have to divide all by x squared. If one was an x to the 5 as the highest power, I'd have to divide all by x to the 5. So I'm going to divide all by x. There it's shown. Simplifies to that. Now immediately I can see as x tends to infinity, that tends to 0, so it's gone. That tends to 0, so it's gone. So we'll end up with that constant over that constant. 2 over 1 which is 2. So there is our horizontal asymptote. A vertical asymptote, well, we're going to find what x must approach for y to tend to infinity. So there we say the limit as x tends to what of that will give us infinity. What value must x go closer and closer to make this bigger and bigger? There we are, -5. Why? Because -5 makes this 0. Now we're not saying x equals -5 for this function. We are saying the vertical asymptote is x equals -5. It's not part of the graph, but the graph is approaching closer and closer to it. Here's another one. So to find the horizontal asymptote, we find the limit. Notice I've divided everything by x squared because x squared is the highest power within the numerator and the denominator. Simplifies to that. Both of those, even though this is x squared, and that's just x, both these will tend to 0, and that'll tend to 0 as x tends to infinity. So I'll end up with 1 over 1, y equals 1, there's your horizontal asymptote. To find your vertical asymptote, we need to factorize the bottom line first. There we are. Now we can see the values of x that make division by 0. So we say the limit as x tends to +1 or -1 will equal infinity or negative infinity. So there are my vertical asymptotes. Horizontal asymptotes, once again the same thing. Now notice that in this case, that's an x squared, that's only an x, must divide through by x squared then, like that. So it gives us that. That is 0, that is 0, that is 0. So ultimately, the limit will end up as being 0 minus 0 over 1 plus 0, and that gives you 0. Now we don't say that's not a number. 0 is a number just as much as any other number. It has just as much as right to exist as anything else. So therefore the horizontal asymptote is y equals 0, the x-axis. Vertical asymptote. I need this to tend to infinity. What must x be? Well, consider it. X squared is positive, therefore x squared plus 16 is positive. This can never ever be 0. Therefore no vertical asymptote. This is an interesting one, just be careful. At face value we'll look at it and say, oh, the vertical asymptote x equals 4. But, there we are. X plus 1, there's no asymptote. But, hang on, we were dividing by x minus 4 originally. We've cancelled out x minus 4s. So we can't say let x equal 4 because then we've cancelled 0 with 0. We've divided by 0 there. It might be gone there, but this is where we started. So we have to say that x cannot equal 4. No asymptotes for that. And note that that is not an asymptote. It's a discontinuity or a hole in the curve, you can say. It's often referred to as a hole in the curve, and you have to be careful to differentiate between asymptotes and holes. Let's sketch a curve. We'll do y-intercept, x-intercept, see if there's any stationary points, second derivative if need be, if there are stationary points, and asymptotes. So y-intercept. Substitute 0, -1. X-intercepts. Equate the function to 0 because y is 0. Multiply through by -2. X equals -2. Let's differentiate. Now remind you, quotient rule. Derivative of the top, 1 times the bottom, minus derivative of the bottom, 1 times the top. All over the bottom, the numerator, squared. And that simplifies to there. Now there is no value of x that is going to make that 0. We need a 0 in the denominator, in the numerator. So therefore no stationary points. So let's go on and find the asymptotes. We're finding the vertical asymptote. The limit of that as x tends to 2 is infinity. Therefore x equals 2 is an asymptote. We're going to find the limit of x plus 2 over x minus 2 as x tends to infinity, which means we're going to write it as the fraction divided by x, divided by x, divided by x, divided by x. And we end up with y equals 1. And that gives us our curve. Another example. 2x squared minus 9 over x squared minus 9. First, the y-intercept. So we substitute 0 for x, and we end up with negative 9 over negative 9. So that's 1. X-intercept, we're now going to equate that to 0. We multiply through by x squared minus 9. We end up with that, and that solves to plus or minus 2, 1. Take the 9 across, divide by 2, so we're finding plus or minus the square root of 4, 5. Differentiate. Derivative of the top, 4x, times the bottom as it is, minus derivative of the bottom, which will be 2x, times the top, all over the bottom squared. Simplifying, we get that. Now for stationary point, we need this equal to 0, so we need the numerator 0. So therefore, to get it to 0, x must be 0. Now we have to find the second derivative. Derivative of the top, there's the negative. Derivative of the top, 18, times the bottom, minus the top times derivative of the bottom. Now this is a chain rule. Multiply by 2 inside to the 1. 2 inside to the 1, and then multiply by the derivative of the inside. Now I don't need to simplify that. I'm now going to substitute 0 into that right at that stage. And I can easily see that it's going to be less than 0, negative. Therefore a local maximum at 0, 1. Asymptotes. The limit as x tends to plus or minus 3 of that will give you infinity. Therefore x equals plus or minus 3. And to find the limit as x tends to infinity, we divide top and bottom by x squared. That tends to 0, that tends to 0. So overall, constant over constant, it's tending to 2. And there is our asymptote there, giving us the graph